Hello everyone and welcome to the Unit 1 AP Chemistry Review. I'm the AP Science Tutor and today I'll be reviewing topics from Unit 1 AP Chem. Just a little note before we begin. I just want to say that this video is something that you should use to refresh your memory. You should already know what each of these topics mean. This is just a review for whenever you have your Unit 1 AP Chem test and you want to refresh your memory a little bit. Anyways, let's begin. So let's start with the structure of the atom. So the atom is made out of different subatomic particles. These particles being protons, P+, that's the symbol. It has a +1 charge. The mass is around 1 AMU, and it's located inside of the nucleus. The number of protons equals the atomic number Z, and it determines the element. Example, carbon always has 6 protons. If you look at the table, you'll see what I mean. It's number 6, it has 6 protons. Neutrons, N0, it has a neutral charge, it has the mass of about 1 AMU, and it's also in the nucleus, and varying neutrons lead to different isotopes. So for example, C12 has 6 neutrons, C14 has 8. So C12 has 6 neutrons. That's just normal carbon, C12, because it has 6 protons and 6 neutrons. So since protons and neutrons make up the weight, it will have an AMU of 12. C14 has 8 neutrons and it would have an AMU of 14. Because 6 protons plus 8 neutrons is 14, and since they both make up the weight, then that would be that. Then electrons, E negative, have a -1 charge. They have negligible mass, which means that they don't count towards the AMU, and in orbitals around the nucleus, they're not in the center with the protons and the neutrons. They control the chemical behavior. And then we have ions. We have cations, which lose electrons, which means smaller radius and less repulsion, stronger nuclear pull. So if you think about it, if you lose an electron, the other electrons are gonna kind of huddle in closer towards the middle, and so therefore the nucleus will have a stronger pull on them. Example, Na to Na plus shrinks because it loses an outer 3s electron. So because it's losing an electron, there's less repulsion between the electrons, and so it kind of shrinks in towards the middle. Anions gain electrons, have a larger radius, added repulsion. Example, Cl to Cl negative grows because of the extra electron in its 3p subshell. So when you gain an electron, there's more repulsion in between each electron, and so the radius grows. Next, we have isotopes and average atomic mass. So definition, atoms of the same element with the same atomic number but different neutrons. So that's what we were talking about earlier with the C12 and the C14. C12 and C14 have the same amount of protons. They just have C14 just has 2 more neutrons than C12. And another example, hydrogen has 3 isotopes: protium H1, deuterium H2, and then tritium H3. And then average atomic mass formula. The average atomic mass formula is average mass equals the summation of fraction abundance times isotope mass. So sample problem right here, magnesium has 3 isotopes, Mg24, 79%, Mg25, 10%, Mg26, 11%. And so basically what you do is you do the fraction abundance times the isotope mass, which in this case is 24 for this one, and then 0.1 times the isotope mass, which is 25 for this one, and then 0.11 times 26, which is the isotope mass for this one, and then you basically do the summation of everything, which means you just add everything together, and that should give you the AMU. And yeah, this matches the mass of magnesium on the periodic table, which is 24.31. so it's around there. And then mass spectroscopy, this is what mass spectroscopy looks like. Peaks represent isotopes, and the x-axis equals mass/charge ratio, mz, and then y-axis equals abundance. And you should already know how to work with these and analyze them and solve problems based on the graphs. Next, we have the mole concept. So, definition: 1 mole equals 6.022 times 10 to the power of 23 particles. And the conversions are grams to moles divided by molar mass, moles to atoms multiplied by Avogadro's number, and gases at SDP are 1 mole equals 22.4 liters. Y'all should know what these transformations mean, or conversions. Anyways, examples. So, how many atoms in 12 grams of carbon, and how many moles in 18 grams of water? So, these are like a little bit more simplified here, but if you want to look at how I did it, so I did 12 grams of carbon in atoms, or 2 atoms. So we had 12 grams of carbon, and then we divide by the molar mass in order to get the moles. And then for the moles of carbon, we divide by the moles again, because 1 mole is 6.022 times 10 to the power 23 atoms, or particles. So once you multiply the top side and divide it by the bottom side, then you would get 6.02 times 10 to the power of 23 atoms of carbon, which yeah, would give the answer to this. So yeah, anyways, next we have percent composition and formulas. So percent composition formula is percent element equals mass of element in 1 mole compound slash divided by molar mass of compound, and then all of that times 100. So right here we have mass of hydrogen equals 2 grams, mass of oxygen equals 16 grams, and then the total is 18 grams. So then you do percent hydrogen, you do 2 grams out of the 18 times 100, which would give you the percent of hydrogen in the compound. And then since you have 16 grams of oxygen, you divide that by 18 and then times 100, which would give you the percent of oxygen in that compound. Then we have empirical formula, simplest ratio, the empirical formula is the simplest ratio of a compound, or of elements in a compound. The example would be 40% carbon, 6.7% hydrogen, and then 53.3% oxygen. So convert to moles. So I'll explain this a little bit later, but you should already kind of know how to go from percent to moles. And then once you get the moles, you would then divide by the smallest, and you will get the empirical formula. The molecular formula is multiple of empirical. So the multiplier equals molar mass given divided by the molar mass of the empirical. And usually you're given the molar mass of the actual molecular formula, and then you can find out the multiplier and then add that apply the multiplier to the empirical formula to get the molecular formula. And then if molar mass equals 180, empirical mass equals 30, then you multiply the empirical formula by 6, which would give you C6H12O6. Because if you do 180 divided by 30, that's 6. So the multiplier is 6, and so then therefore you apply it to the empirical formula. For hydrates, example, 5 grams of copper sulfide, or 5 grams of CuSO4 times X, which is what we're trying to find, H2O, is heated, and then only 3 grams left of that compound is left. Basically, when you heat it, you get rid of all the waters inside of the crystals of the hydrate, and so you're just left with whatever isn't water. And so the mass of the H2O can be found to be 1.8, because if you do 5 if you do the 5 grams of the hydrate minus of just the compound, since there's no water left here, then you would get 1.8 grams, and then that would give you 0.1 moles of H2O using stoichiometry, and then you figure out that you have 3.2 grams of the compound left, as stated up here earlier, and you divide that by its molar mass, and that should give you the amount of moles of the compound. And once you have that, you divide everything by the smallest, so this would end up being 1 for its number here, and then if you do the water, you do 0.1 divided by 0.02, you would get 5, and then you would find out that you have 5 H2O in the formula. So next you have the steps to solve the empirical formula. That's what I was talking about earlier. You do percent to mass. So the easiest way to convert percent to mass is to assume a total of 100 grams. For example, 42% is 42 grams. And then mass to mole. So be sure to leave your answer in at least 4 sig figs to maintain your accuracy. And then you divide by the smallest, which we were talking about earlier. You divide by the smallest, so you get the empirical formula. And then there are times when the empirical formula will not have whole subscripts, and so depending on what the numbers are, you would multiply by 2, 3, 4, or 5. So that just depends on what you get as the subscript. So it says if all of the results in number 3 are not whole numbers, some of them are decimal/fraction numbers, you must multiply all of the results in number 3 by some number which will make everything a whole number. If the decimal portion is this, then you just apply those multiplications to the thing to make the compound have whole subscripts. And then you have to memorize the saying, percent to mass, mass to mole, divide by the smallest, multiply till whole. So that saying really helped me out on my test, and my teacher always stressed the fact that we should memorize it, since it's a really helpful saying. So percent to mass, mass to mole, divide by the smallest, multiply till whole. Just remember that, and you should be fine. Anyways, electron configurations. So we have the rules, orbital diagrams, and EC. So electron configurations. The Aufbau rule is that electrons are placed in orbitals of lowest energy amount first. Remember, things can get a little weird with D and F filling order. If elements are out of order, it could possibly be because an electron has become excited. Pauli, each orbital can only hold 2 electrons, and no 2 electrons can have the same 4 quantum numbers. Even if energy level, sublevel, and orbitals are the same, the spins will be different. The particles, the 2 electrons, cannot be the same. They have to have a difference in between them, so the spins will be different. Hund, when filling a sublevel which contains orbitals of equal energy, one electron enters each orbital with the same spin direction before they double up. So the rule is that you have to apply like you can see the boxes right here. You have to apply an electron of the same spin in each box before you can double up and add the downwards arrow. So you have to fill up each box, and then you can start doubling up from the first one. Examples of electron configurations: you have oxygen, which is the full electron configuration, 1s2, 2s2, 2p4, and then you have sodium, which uses the abbreviated electron configuration, which you should know what it is. Is you go to the nearest noble gas, and then you go from there to the element that you're searching for. And then you have the chromium exception and the copper exception. This isn't really something that's really important, but I mean, it's good to know that there's an exception for chromium and copper. And then orbital diagrams, boxes plus arrows for spins is this, what I was talking about earlier. So yeah, next we have Coulomb's law. So the equation for this is F equals K Q1 Q2 over R squared. You should have learned about this and what it means. So you don't really need to use the equation. You just have to understand what the equation means. And so for large nuclear charge equals stronger attraction, because since this is a fraction, if the top is bigger than the bottom, then it's gonna be a whole number, and if you just keep increasing the top, then it's just gonna be a bigger and a bigger number. If you have a small radius, it means a stronger attraction, because if you decrease the bottom part of this fraction, then the number will keep getting bigger and bigger, and so the force will increase and increase. So if you increase the top, force increases. If you decrease the bottom, force increases. So that's what it means. A large nuclear charge, the Q's are the charges, and so if you increase the Q's or the nuclear charge, the force increases, so stronger attraction. That's what it means. And then if you decrease the bottom, the force also increases, which means stronger attraction, because in a fraction, if you decrease the bottom, the number increases. Explains why ionization energy increases across a period, more nuclear charge, why anions expand, more repulsion, and why cations shrink, less repulsion, stronger pull. So next we have periodic trends. We have atomic radius, which when you go across, you have a stronger nuclear pull, so atomic radius decreases. When you go down, you have more shells, so atomic radius increases. Then you have ionization energy, so when you go across, it increases because there's more protons in the nucleus, and so therefore the pull on its electrons is greater, and so it's harder to pick off those electrons from the electron shells. And if you go down, you have more electron shells, which means a lower ionization energy, since it's easier to pick off those electrons the further away they are from the nucleus, since the attractions aren't as strong. Example is magnesium, and we have a magnesium atom right here. So as you can see, magnesium has 2 electrons on its outer shell, one here and one here, and so basically, the ionization energy for these 2 electrons right here would be low because they're the furthest away from the nucleus, and so the nucleus doesn't have that strong of a grasp on them since they're further away. There's not as much attraction. But when you get to the third electron, for example, this one right here, if you were to try to pull it off, it would take way more energy since it's closer to the nucleus, and since there's more attractions. And so therefore, this one would have a higher ionization energy since it's closer to the nucleus. Then we have electronegativity. You just have to, for the most part in AP Chem, you just have to remember that fluorine has the highest electronegativity, and so you just, when you reason it on your FRQs, you just have to know that if you go across, your electronegativity increases, and if you go down, your electronegativity decreases. And then for ionic radius, cations are smaller, anions are larger. We talked about that earlier in the video. And we have example, Na radius is smaller than Na because it lost an electron, so the repulsions there's less electron repulsions in the shell, so the structure decreases. And then the Cl negative radius is greater than the Cl because it gains an electron, and so there's more electron repulsions in the shells, and so the radius increases. So cations lose electrons, anions gain electrons. And then you have PES, or photoelectron spectroscopy. So it measures the binding energy of electrons. A graph equals peaks for each orbital. Height equals number of electrons. Example, lithium 1s2 peak at high binding energy, 2s1 peak at lower binding energy, because the electrons are further away. And same for carbon. And then here's a table. So basically, this is a PS graph for fluorine. The what do you call it? The electron configuration formula for fluorine would be 1s2, 2s2, 2p5. As you can see here, 1s2, 2s2, 2p5. So we have the binding energy at the bottom and the relative number of electrons, which is the y-axis. So as you can see here, the 1s2 electrons have a really high binding energy, and that's because they're the closest to the nucleus, so there's a lot of attraction. The 2s2 has less binding energy than the 1s2 electrons, because they're further away from the nucleus. And same here for 2p5. There's less binding energy because they're even further away from the nucleus, and so there's less attractions. And as you can see here, in the 1s2 in the 1s orbital, there's 2 electrons, hence why it's at the second line. In the 2s orbital, it's 2 electrons again, hence why it's at the second line. And if you remember, for the 2p orbitals, the max electrons they can have is 6, but since fluorine only has 5 electrons there, that's why it's at the 5th line. And finally, we have essential equations for Unit 1 of AP Chem. So we have average atomic mass, which is the summation of the abundance times the mass of the isotopes. Then we have moles, which is grams divided by molar mass, and particles divided by Avogadro's number. Then we have percent composition, which is percent equals part over whole times 100. Then we have the empirical formula, which is dividing mole ratios like we talked about earlier. And then we have Coulomb's law, which is F equals K times Q1 times Q2 over R squared. And on a separate note, you need to know that you don't need to, on your AP test and on your unit test, you don't need to use this equation along with numbers to solve problems. You just got to know the concept of this equation, which we talked about earlier. And yeah, you also need to know metric prefixes for using stoichiometry. And you should already know how to do this from your advanced chem or your on-level chem that you took. And yeah, anyways, if you enjoyed this video, please like and subscribe, and yeah, see y'all next time.